Good afternoon, everybody, online and in person. Thank you for attending. It is really with great honor that I get to introduce Professor Will Burns, who is a world-renowned expert and thought leader on international environmental law. Dr. Will Burns is the Associate Director of the Environmental Policy and Culture Program at Northwestern University, as well as the founding co-director of the Institute for Responsible Carbon Removal at American University. And he's here today to discuss regulatory regimes to manage ocean-based geoengineering options. Will Burns?
Thank you, everyone, and thank you for coming. And I'll get right into this so that we can leave some time at the end for questions. And so, first of all, just a little bit of setting of the table about why we even talk about these options. So, as all of you know, in 2016, we established it came into force, at least, the Paris Agreement. And the Paris Agreement establishes the salutary goals of trying to hold temperatures to, quote, well below 2 degrees Celsius, and at least aspirationally 1.5 degrees Celsius. And the way that Paris seeks to effectuate this are through pledges that are made by the party states called nationally determined contributions, right? Pledges to reduce their emissions or mitigate in various ways. Unfortunately, if we map the pledges that countries have made to date against what would be necessary in terms of mitigating emissions, we see there's a yawning gap. And so instead of holding temperatures to well below 2 degrees Celsius or 1.5 degrees Celsius, recent research indicates that we're on track for temperature increases of somewhere between 2.7 and 3.1 degrees Celsius by the end of the century and beyond. And what we know is that temperature increases of this sort could be catastrophic, both for human institutions as well as ecosystems. And as we move to the higher temperatures, these impacts become much more severe and in many ways in a non-linear sort of fashion. What we also know is that these kind of temperature increases will have extremely serious impacts. For example, if temperatures rise by 3 degrees Celsius by the end of the century, it will melt the entire Greenland ice sheet. And the loss of that ice mass alone will result in sea level rise of about 7 meters or 20 feet. Right? The good news is it'll take about 1,000 years for that to happen. The bad news is that we would then be locked into that sea level rise for about 5,000 years thereafter, right? One landmass. Second of all, we're extremely worried that if temperatures rise by 2 degrees Celsius, we'll likely lose all of the world's coral reefs, which provide critical sustenance for about 1/5 of all ocean-based species. The Intergovernmental Panel on Climate Change says that if temperatures rise by 3 to 4 degrees Celsius, 60% of all the species on Earth would be potentially threatened. We'd also see substantial declines in agricultural production, especially in some of the most vulnerable countries, increases in disease vectors, increases in violent weather events. And so, as a consequence of this, and the fact that the world community has not been able to get its act together in terms of reducing emissions, and the so-called legacy emissions that reside in the atmosphere now lock us into extremely high temperature increases, we've started looking at other options besides simply reducing our emissions. One of them that we've been looking at in earnest are carbon dioxide removal options, or CDR. And I just want to start off with a working definition, right? CDR are human-based activities that seek to remove carbon dioxide from the atmosphere, durably store it. Durable is a term that's contested how long it is, but it's somewhere from 100 to 10,000 years for most people, in geological, terrestrial, or ocean reservoirs, or in products, okay? And we'll talk more about all of this in a moment. The other thing that we know now is not only do we need carbon dioxide removal, but we need it at an extremely large scale. Again, because of our ongoing emissions and the emissions that are already residing in the atmosphere. So according to the Intergovernmental Panel on Climate Change, as well as a number of other studies, by the middle of the century, we are likely going to need beyond decarbonizing the economy as much as we can, sequestration, removal of CO2 from the atmosphere at a level of about 10 gigatons or 10 billion tons a year. And by the end of the century, somewhere between 15 to 20 billion tons, right? And on an ongoing basis annually. Now, up until a couple of years ago, most of the focus in terms of carbon removal options were on terrestrially based options. Everything from trees, as well as direct air capture, which is a technology that is very prominent here at Arizona State, enhanced rock weathering, bioenergy with carbon capture, and so forth. But what we've come to realize in recent years is for technological reasons, for sustainability reasons, for economic reasons, these terrestrial approaches are not going to be sufficient in terms of reaching these goals of 10 to 20 gigatons a year of carbon sequestration. And so researchers and policymakers have increasingly turned to the potential role of the world's oceans in terms of atmospheric carbon removal. And looking at the oceans makes some sense because the oceans already perform a yeoman task in terms of carbon removal, right? As you can see here, there is 50 times more carbon stored in the world's oceans than there are in the atmosphere, and 15 to 20 times more carbon than in all land, plants, and soils combined. Okay, so the purpose of this presentation is to very briefly talk about what some of those primary marine-based carbon removal approaches are, and if we are to go down this path, how might we potentially govern these, at least primarily at the international level. And that's what I'm going to focus on. So first of all, let's talk about the primary marine carbon removal approaches. And for each one of these, I'm going to try to look at the science behind them, the potential benefits, the potential risks, and the prospects moving forward. But again, very quickly. So the first of these approaches that we look at is ocean iron fertilization, or OIF, right? The idea of OIF starts with phytoplankton, right? Single cell organisms in the oceans. Phytoplankton, of course, take up carbon dioxide in the photosynthetic process, as do land-based plants. And indeed, half of all the photosynthesis that occurs on Earth occurs in the world's oceans. Now, taking up CO2 from the oceans does nothing in itself to remove CO2 from the atmosphere. But the idea is that as the phytoplankton take up CO2 and reduce the amount of CO2 in the oceans, it changes the pressure differential between the atmosphere and the oceans, and it allows more atmospheric CO2 to enter the oceans, which means there's a net drawdown of carbon dioxide from the atmosphere. And that's the fundamental premise behind ocean-based fertilization. Ocean-based fertilization occurs in a process called the ocean's biological pump. And the idea is that when the phytoplankton take up the carbon dioxide, most of that carbon dioxide is almost immediately released at surface when the phytoplankton are consumed by zooplankton. But a small portion of that carbon dioxide stays with phytoplankton when they die, drop below the photic or light layer, and ultimately end up in sediments. And at this point, it potentially for 1,000 years or more, that CO2 that's been locked up by the phytoplankton can remain locked up and inaccessible from the atmosphere, facilitating a drawdown from the atmosphere. And that's the idea behind this ocean process. Proponents of ocean iron fertilization argue that there are certain areas of the oceans, primarily in the Southern Ocean, that have optimal levels of macronutrients for phytoplankton growth, that being primarily magnesium and phosphorus. But they argue that there's a critical shortage of a micronutrient, and that micronutrient is iron. And so proponents of ocean iron fertilization argue that if we were to seed areas such as the Southern Ocean and some areas in the North Pacific and the Atlantic with iron filings, it would stimulate phytoplankton growth. It would essentially put the biological pump on steroids. It would draw down ultimately far more carbon dioxide from the atmosphere. okay? Early modeling, and this is what we had at the outset, indicated that this could be potentially a remarkably effective approach. Some of that modeling indicated that we might be able to draw down as much as 25% of all of the CO2 in the atmosphere, and to do it for somewhere between $2 to $5 per ton, right? But there's two questions that have to be asked. The first of them is that really true? Is it likely to be effective, right? And this is one of the few ocean-based approaches where we actually have a fair amount of field-based data. In the last decade, there were 13 ocean iron fertilization experiments where areas were seeded with iron to test what happened, right? And the results, to put it mildly, were mixed and for the most part disappointing. Right. So first of all, the good news was that a lot of these studies showed that when you seeded the world's oceans with phytoplankton, indeed, you did get a proliferation of algae, phytoplankton. And that's what we want, right? Because there are more phytoplankton taking up more carbon dioxide, right? That was the good news. The bad news is that in virtually all of those studies, other than one, virtually all of that carbon dioxide was lost at surface, right? Well, essentially what happens is when you have a proliferation of phytoplankton, you create a gigantic sushi bar for zooplankton, right? And zooplankton took up most of that phytoplankton, and you saw a release of the CO2. And unless it sinks below the photic or light layer, it's not going to be inaccessible, and you're not going to get carbon drawdown, right? So as these studies have been released, the estimates of what ocean iron fertilization could do have been steadily ratcheted down. One recent study said perhaps you could reduce atmospheric levels of CO2 by 10%. Another said 5%. Some are in the 3 to 4% range, right? Proponents respond in a couple of ways. First of all, they say if it turns out only to be 10%, that's still good, and makes sense that we might want to look at that, because at the end of the day, when it comes to carbon removal at the kind of scales we're talking about, we're going to need a portfolio approach, right? We're going to have to cobble together a bunch of land-based approaches and ocean-based approaches, each at a gigaton or more levels to get to those levels. And if 10%, maybe even 5% would be worth doing. The second thing they argue is that we need more research. We haven't adequately characterized this approach. We haven't done it long enough. Perhaps we aren't doing it in the right areas, right? And so they argue that we need more funding in this context. But funding to date has not really borne itself out. Okay, so the second question associated with this is, are there any potential negative ramifications of putting large amounts of iron filings in the world's oceans, right? And as you could guess, the answer is yes, right? And there's a couple of things that we're primarily worried about. One is what kind of phytoplankton we ultimately get. Let's pretend that this is successful and you get a proliferation of phytoplankton. The bottom line is that you don't get to choose what kind of phytoplankton you get. It's not like going to Macy's, choosing a kind of sock based on the pattern and the color that you want. You get what you get, right? And one of the things that we worry about is that there would be proliferation of phytoplankton species that are unpalatable to the zooplankton in the area. And then you could potentially have a biological trophic cascade, right? If the zooplankton cannot eat the phytoplankton, those populations decline, and then the species that rely on the zooplankton in turn start to decline, right? And we have some empirical evidence that this could happen. In the Antarctic, one of those ocean iron fertilization experiments, we saw a massive proliferation of one kind of phytoplankton called Phaeocystis antarctica. And it outcompeted other phytoplankton, quickly grew in the area. Zooplankton wouldn't eat it, right? Did not matter because it was a very small experiment. We simply stopped, right? But if we were to do this at a basin-wide scale, right, many scientists believe we could potentially have irreversible ecological impacts. And so that's certainly something that needs to be assessed far more than it has. Another thing that we worry about in the context of ocean iron fertilization is something called nutrient robbing. If you look at the Southern Ocean, for example, a lot of the nutrients, the macronutrients in the Southern Ocean, ultimately drift north into fisheries that are extremely large and extremely important in those areas. Now, what happens if all of a sudden you have a massive increase in phytoplankton in the Southern Ocean? Well, they're going to take up a lot more of those nutrients, and instead of them migrating, and they're going to rob these other areas of those nutrients. And that has a number of implications. First of all, as I mentioned before, it could mess up some incredibly important fisheries. It could create geostrategic conflicts as a consequence. It also may mess up any benefits you get from this, right? Because if there's declines in phytoplankton in those other areas as a consequence of the nutrient robbing, you're going to see decreases in the drawdown of CO2 in those areas. We need a lot more research about whether nutrient robbing will occur and at what level it will occur before we could ever do this. And of course, the last thing that we worry about with ocean iron fertilization is eutrophication, right? You're trying to induce algae blooms in this case, right? But it could potentially have negative impacts in terms of the ecosystems. Perhaps less so when we're talking about the open ocean, but still definitely an area of concern. Okay, so that really was the original MCDR approach, or marine-based CDR approach that we focused on. But we've now moved on to look at a number of different other approaches, and so I want to briefly discuss those also. One that is receiving a lot of funding at this point is something called ocean alkalinity enhancement, or OAE. So when carbon dioxide is taken up in the oceans from the atmosphere, it reacts with water and it forms carbonic acid. This carbonic acid in turn dissociates into hydrogen ions and bicarbonate ions. And bicarbonate ions are taken up by shell-forming species, ultimately to form calcium carbonates. And when that happens, it effectively locks up that CO2. And then when those species die, again, much like ocean iron fertilization, and drop to the bottom of the ocean, that CO2 can be locked up in sediments, again, potentially for thousands of years. Unfortunately, the increased carbon dioxide that's entered the oceans in recent years as a consequence of increased greenhouse gas emissions have saturated this and have slowed down that process, right? So the idea of ocean alkalinity enhancement is to add alkalinity to the oceans to speed up this process again, right? And this is the chemical explanation of how that would happen. And so we've started looking at adding things such as olivine, wollastonite, limestone, right, to induce alkalinity and try to convert more CO2 into bicarbonates that are ultimately stored in the world's oceans. Now, there are a number of questions associated with this approach also. One question is how effective it would be, right? And the studies are all over the place, right? Some studies say that we might at the most draw down atmospheric concentrations of CO2 by about 30 parts per million, and we're at about 420 right now. Other studies, though, on the other end say it could be somewhere between 160 to 450 parts per million, right? And obviously that could have dramatically positive impacts, right, in terms of climate change. But when you have error bars like that, right, between 30 and 450, right, it indicates that there's a lot you don't know, a lot of methodological assumptions that still have to be teased out, right? So the jury is out in terms of the effectiveness of this approach. We're also worried about risks associated with alkalinity enhancement. One is alkalosis, right? There may be certain species, and there's some preliminary evidence that certain species such as littoral crabs may not be able to adjust to rapidly increasing levels of alkalinity in the oceans, right? So we need to characterize what areas in the ocean we might not want to do this. We have to characterize how quickly we do this and at what levels of application to avoid any of those potential negative impacts. Also, the addition of some of these minerals, especially things like olivine, could also result in the release of heavy metals, things like nickel and chromium, right? And we're worried about those impacts in terms of organisms. Now, the good news is that some of the preliminary field research that's been done in this impact has indicated that the heavy metal levels do not reach levels that are toxic for most organisms, right? But we're at very early stages, right? We need temporally these studies to be much longer. We need much larger applications of alkalinity to be able to make those determinations and ensure that we're not messing up the world's ecosystems. We're also worried about biogeochemical impacts. One study said that adding one kind of alkalinity, calcium hydroxide, could change the timing of phytoplankton blooms and lower zooplankton biomass overall, right? And that could have all kinds of impacts in terms of the architecture of the food chains in the world's oceans, right? So again, another area for research. A third approach we're looking at, ocean upwelling and downwelling, and I'll focus on upwelling because it's the one that's discussed the most. And this one's easy to understand. The idea here is to use a process such as a series of pumps to pump nutrient-rich materials from the bottom of the ocean to the top of the ocean to stimulate phytoplankton, right? And so again, this is a phytoplankton fertilization sort of project, right? More phytoplankton proliferate, they take up more CO2. Number of questions associated with artificial upwelling, however. One is how effective it would be, right? Some studies say that maybe at the most, it would draw down a gigaton, 1 billion tons of CO2 a year. Which might be worth it, right? Other studies say there would be much less, right? So we need a lot more ongoing sort of field research to make that determination, right? We're also worried about some of the risks associated with this. One is that it potentially could restructure ocean ecosystems, right? It could ultimately, by introducing these nutrients, favor the production of large phytoplankton, such as diatoms, right? And it could shift the ecosystem in ways that would favor some species and disfavor others that consume different kinds of phytoplankton. And again, another area of research. Another thing that we're worried about is that at the bottom of the ocean, there are a lot of nutrients, but guess what else there is at the bottom? A lot of CO2. Right? And so we're worried that by ultimately upwelling these nutrients, we would outgas massive amounts of carbon dioxide at surface and ultimately into the atmosphere, right? And some of the preliminary modeling indicates that that's a very real risk, okay? Two more approaches. Macroalgae cultivation or seaweed farming. Now, seaweed's been growing in the world's oceans for at least 500 million years, right? And natural seaweed takes up about 170 million tons of carbon dioxide annually. So proponents of seaweed farming argue that if we could massively increase the cultivation of seaweed in the oceans, they would take up huge amounts of CO2 through the photosynthetic process, and then ultimately that seaweed would drop to the bottom of the ocean and be buried in sediments. And so one company, for example, has proposed that they use buoys, that they would seed with seaweed, and that as the seaweed grew, ultimately those buoys would become very heavy and they would sink to the bottom of the ocean and take all of that carbon dioxide with them, right? And they've estimated that ultimately they could sequester between a billion and 2 billion tons of carbon dioxide annually, right? Which again could definitely make this approach worth it. However, there's a lot of skepticism about whether those claims are true. A recent study by the National Academy of Sciences of marine carbon removal indicated that if you were to seed all of the world's coastal areas that could be seeded with seaweed, which is approximately 20% of coastal areas, that you would only get about a third of a ton of 1 billion tons of sequestration, right? And we're not really going to seed all 20% of those coastal areas with seaweed, right? But even if you did, it's a relatively a small number. Okay, that's one issue. Another issue are the risks associated with doing this. right? One of the problems is that seaweed, if it is growing, competes with phytoplankton for nutrients, right? And so, and competes quite effectively with phytoplankton for nutrients. So one recent study said that as a consequence, we believe that if you did large-scale seaweed farming, you potentially reduce the amount of phytoplankton in the world's oceans by a fifth by 2100 and 60% by the year 3000, right? And so there's two implications there. One, phytoplankton are at the base of the food chain, right? So you have all kinds of potential ecological implications of that. And second of all, to the extent that phytoplankton take up large amounts of CO2, that offsets a lot of the benefit that you get in terms of this approach, right? And that's definitely an area for additional research. And then the last thing that we're worried about is what are the implications for benthic or bottom organisms when you drop huge masses of seaweed biomass in those areas, right? We'd have to be very careful in assessing the benthic ecosystems and where we could do this that would be most propitious, right? And that's going to take time and money, research requirements also that haven't been done. The last thing, and then I'm going to get into governance, that is a concern for all of these issues, is something very wonky called MRV, monitoring, reporting, and verification, right? If you as a country are going to claim that part of the way you're meeting your pledges under the Paris Agreement is by sequestering CO2 in the world's oceans, you're going to have to quantify how much sequestration is being effectuated. If you're Microsoft and you're buying ocean alkalinity credits to apply toward your net zero commitments, you're going to have to prove pretty precisely how much CO2 is being taken up, right? The problem is that is very difficult in an extremely large, open, variable ecosystem like the world's oceans, right? Take ocean alkalinity enhancement just as a case study. If you put olivine in a certain part of the oceans, it may be that where that air-sea flux exchange happens, right, where ultimately the CO2 is reduced in the oceans and then drawn down from the atmosphere, may occur hundreds of miles from where your intervention occurred. It may also occur years after you did it, right? And you may have major problems in terms of the signal to noise ratio because there's lots of other factors in the ocean that simultaneously may have been drawing down CO2, right? So establishing how much and that your intervention is what caused that change in air-sea flux is a major challenge, right? And it's something that lots of researchers are looking at, but they haven't cracked the puzzle in most people's minds, and it's probably going to be very expensive, right? Which will add to the costs of these processes. All right, very quickly then, let's decide we're going to do this, right? We're at least going to engage in the research, and we're going to potentially deploy these approaches. Virtually all of these approaches that we've talked about could have positive impacts in terms of climate, but they could also have lots of impacts in terms of the global commons or other countries, right? And so that necessitates international regulations and to some degree consensus about whether we should do this. And so the question is, what regimes at the international level could potentially regulate this? Well, to date, there's been two of them that have tried to do that to some degree. The first was a treaty called the London Convention. So the London Convention was designed in 1972 to address dumping of materials into the world's oceans. When we realized how dangerous it was to dump a lot of toxic chemicals on land, Times Beach, Love Canal, we could have started reducing the amount of toxic chemicals we were producing, but we're humans, so we didn't do that. We said, where else can we dump it, right? And then by the time we got to the 70s, we were like, oh, that's bad too, right? So we need a convention to regulate what's being done. Well, in 2008, the parties to the London Convention became alarmed when ocean iron fertilization experiments began, including by commercial ventures, right? And so they passed a resolution to try to regulate ocean iron fertilization. And it was a good news, bad news story if you're in that industry. The good news is there's an exception under the London Convention that says that if you're putting materials in the ocean for a purpose other than mere disposal, then it's not dumping as long as it comports with the rest of the treaty, which is to protect human health and marine life, right? So the parties said, well, if you're putting iron in the ocean, you're not putting it in the oceans to dispose of it, right? You're trying to take down CO2, right? So it looks like it can fall under that exception. But remember, it also has to comport with the rest of the treaty and protect the species that we're concerned about and human health. And we know very little about the impacts of ocean iron fertilization, right? So here's what we're going to say. You can engage in this and it won't be dumping as long as you do it just for scientific research purposes. In other words, you can't be selling carbon credits to Microsoft or to governments. It can only be for scientific research, and it's subject to risk assessment, right? And then in 2010, they had set up a risk assessment framework. And any of you that have had classes in risk assessment, right, this is the traditional elements of it, okay? And the government that has jurisdiction over the operation, the university or the company, then has to sign off on that risk assessment that it's warranted. Okay, and that's what London said. Now, there's real limits to this treaty's ability to regulate these approaches. First of all, it was restricted to ocean iron fertilization, right? So it doesn't regulate ocean alkalinity enhancement or any of the other approaches that we talked about, right? That's limit number one. Limit number two to this approach is that the resolutions that are passed by the parties to the London Convention are not legally binding on the parties, okay? Now, most of the parties adhere to most of the provisions of most of these resolutions most of the time, okay? But they don't have to, right? And that's another limitation. And that's created a lot of trepidation about whether this was ultimately going to be able to do anything. Well, fast forward, we have a successor treaty to the London Convention called the London Protocol that was established in the 1990s. It's more precautionary. It's more science-based, based on what we had learned in 20 years. And the idea of the London Protocol is that once all of the parties to the London Convention ratify this new treaty, the London Convention goes away and the protocol governs all dumping operations, okay? But until then, they operate in parallel. So the London Protocol passed a resolution that amended the treaty in 2013 to include all potential marine geoengineering activities, right? And then it required you get permits for those activities, right? And then it established and it limited it to limited legitimate scientific research. And then it established a risk assessment framework, right? So it looks a lot like the resolution, right, that we passed in 2008 under the London Convention, but there's a couple of major differences. First of all, because this is an amendment to the treaty's language, it is legally binding when it comes into force, unlike the resolutions that they pass, right? Second of all, it contemplated that all marine geoengineering activities could be regulated, right? It doesn't do it initially. It has an annex called Annex 4, and any marine geoengineering approach that's put in Annex 4 is then subject to these requirements, right? Of only legitimate scientific research and risk assessment. And the only one that they put in Annex 4 initially was ocean iron fertilization, right? But they could expand it in the future, right? So it's much broader in its potential scope than the London 2008 resolution, right? And so that's what the parties did. But this has some real major limitations too, in terms of the parties. First of all, obviously, number one, it's initially only focused on ocean iron fertilization, right? Though, of course, it could be expanded in the future to other approaches. Second of all, it requires to come into force, to be legally binding on the parties, 2/3 of the parties to accept it, right? That's roughly 37 parties. There's 53 parties in the London Protocol. So you need 37. Right now we have 6. right? So we have a long way to go before that comes into force, okay? Third major problem is a very small country that would have no significance to these approaches is not a party to this treaty, and that's the United States. And I'm being facetious because most of the marine carbon removal companies and research is happening with US-based entities, right? US is not a party to the London Protocol. We're a party to the convention, but not the protocol. And there is no way in hell we are going to join a new treaty, at least in the next few years, right? So that treaty does not apply to us, okay? And that's another major limitation of this. Now, fast forward, the parties to the protocol and convention have been quite kinetic. They've responded to the fact that we're now researching other approaches, right? Ocean alkalinity enhancement and upwelling and seaweed farming. And so they passed a resolution in 2023 that said a couple of things. One, we may have to now place in Annex 4 other ocean-based approaches other than ocean iron fertilization. And the two on the carbon removal side that they targeted were ocean alkalinity enhancement and biomass cultivation for carbon removal, right, which would be seaweed. Okay, and so that's one way that the treaty's purview could expand. Second of all, they said that in the interim, even before this amendment comes into force, the parties should provisionally apply it when it comes to any marine geoengineering approach, right? So, and that can be done under the treaty. So even though it's not into force, if you agree that it'll be provisionally applied, the parties should apply it. And so all these provisions would apply, okay? And that's what London did. Very quickly, the CBD, the Convention on Biological Diversity in 2010, passed a resolution that looks almost identical, right? You can only do it for scientific research purposes. You can only do it with risk assessment. Limitations of the Convention on Biological Diversity are several. One, its resolutions are not legally binding on the parties, as was true at the London Convention. Second of all, a very small country is not a party to it, and that's the United States, right? So again, this is not going to be binding on any U.S. company or academic entity. Other treaties that might apply in the future, the United Nations Convention on the Law of the Sea. The Law of the Sea provides for a right to conduct marine research, right? So it could, in theory, privilege us to research these approaches that we're talking about in more detail, right? But it also has some major limitations. If you're going to do that kind of research in coastal areas or within 200 miles of a nation's coast, you're going to have to let that country participate if it wishes, or establish regulation of how that scientific research occurs, right? Which could limit where this research occurs and how this research occurs. In the open oceans, again, Article 257 says pretty much you're supposed to privilege marine scientific research, which would be good for this kind of research. But it also provides that there can be liability, meaning that if you damage the world's ocean ecosystems through research, you're liable for damages, right, to those that are potentially hurt by it, right? If you do this at a very large scale, then ultimately you're going to be subject to the marine pollution provisions of the Law of the Sea Convention, right? Article 194 says you should prevent, reduce, and control pollution of the marine environment from any source, right? And pollution is defined as substances or energy which are likely to result in deleterious effects, right, to living resources or marine life. If one were to construe, for example, olivine releasing heavy metals that affected ocean organisms, it could be deemed a pollutant. And if a country did not prevent, to the greatest extent that it could, that kind of pollution, it could ultimately be held responsible and liable for any damages that occur, right? Same thing with nutrient robbing or any of the other things that we talked about, right? And the Law of the Sea Convention has a tribunal called the Tribunal for the Law of the Sea that can hear cases of this nature, right? So that you could see adjudication in the future. A new treaty that's been established under the law of the Sea Convention may be applicable in the future. Biodiversity beyond national jurisdiction. This is a new treaty that hasn't come into force, but probably will in the next couple of years. Most countries will probably join it. We won't, okay? But most other countries will, and it'll be applicable to them. It'll have provisions that will be important, in my opinion, for marine geoengineering. One will be the fact that they can establish marine protected areas and other kinds of area-based protections. It may be that certain areas will be excluded from marine CDR, right? It may be other areas are privileged for it, right? For example, ocean alkalinity enhancement could also potentially help us combat ocean acidification, right? And if we have areas of high acidification in those protected areas, we might actually privilege ocean alkalinity enhancement, right? But this will be a treaty that may help us to sort out some of those issues where spatially, temporally, we would deploy these approaches. It also has a pretty stringent environmental impact assessment process, which requires that you screen for activities that potentially have large impacts, and for novel approaches, especially, right? And to the extent that marine CDR is by definition a novel approach, it's likely you're going to see environmental impact assessment requirements. And those impact assessment requirements include report and review to the scientific body of the BBNJ that also gets to weigh in as to whether they think this should be done, right? Which could influence the nature of those projects moving forward. And then finally, the Paris Agreement, right? Obviously, the climate agreement should have some role in this, and it could, right? Paris in Article 4 says parties are to pursue domestic mitigation measures, and mitigation is defined under the parent agreement to Paris as limiting emissions and enhancing sinks. Sinks are things that take up CO2, right? So it's pretty easy to say that the parties could, as part of their pledges, their NDCs, include carbon dioxide removal in their pledges, right? And marine carbon removal may be part of that, right? So it could be part of effectuating the goals of the Paris Agreement. Also, there's language in the Paris Agreement that says that parties can be affected not only by climate change, but by the impact of measures taken in response to it, right? And so one could argue that MCDR is a response to climate change, right? And what the preamble says is that you should acknowledge that climate change is a common concern of humankind, and when you take action to address climate change, you have to respect, promote, and consider obligations on human rights, right? Well, if an argument was made, for example, that it would wreak havoc with fisheries, you could be contravening the human right to food. You could be contravening the human right to subsistence, right? And it may be that some of the parties seek to invoke those provisions to limit where these approaches are deployed, which approaches are deployed, at what scale these approaches are deployed, right? Hard to know. This is language in the preamble. It's the introductory section of the Paris Agreement. It's not legally binding on the parties, but it provides guidance in terms of how you implement the treaty. And so it could be relevant in the future. And then last thing, there's going to be domestic law that regulates these things. Some of these approaches are going to be deployed primarily in coastal areas. And just as an example, in the United States, these are some of the laws that potentially would be relevant to regulating these approaches. Mining laws, if you're going to mine wollastonite or olivine, for example, to use it for ocean alkalinity enhancement, the mining laws, including the health regulations, environmental regulations, are going to be pertinent to these approaches, especially if you're going to do it at that kind of scale, right? Because it would require huge amounts of these materials. The Marine Protection Research and Sanctuaries Act regulates the dumping of materials into U.S. coastal waters, right? And it implements the Paris Agreement in the United States, but it doesn't have that dumping exception. It says anytime you put something in the ocean, it's dumping, right? And that may have influence as to whether companies want to pursue it, whether investors will provide funding for something that the government says is dumping into the ocean, right? There's all kinds of things, so how that law may influence things. The Clean Water Act the Coastal Zoning Management Act and the National Environmental Policy Act, which regulates a large-scale sort of projects, right, and requires risk assessment, environmental assessment, would also likely be pertinent in this case, right? And in a lot of cases, a lot of these approaches never even contemplated, right, an approach of this sort. Really, they were basic pollution regimes. And now we're saying putting things in the ocean is actually good for you, right? How do pollution regimes deal with that kind of intervention, right? It's going to be a major cultural challenge for a lot of those agencies, not only in the United States, but in any other country where we deploy these. Okay, so I'm going to stop there and say it's likely that as we continue not to get our act together in reducing our emissions, maybe even increase them in the next couple of years, given politics, it's likely that the drumbeat for carbon removal approaches is going to get ever louder. And one of the components of that is likely to be marine-based approaches, right? And I think it's important to understand the potential risks, the potential benefits, and how we as society might seek to govern these moving forward. Thank you very much.